Hey guys, this is section 6.11, the equilibrium constant in terms of mole fraction or molarity. So we'll start out with our generic equilibrium reaction, AA plus BB, in equilibrium with CC and DD. We've seen before, we can write Kp is equal to this expression right here, partial pressure of each component over the standard pressure raised to the power of their coefficient, the products on top, reactants on the bottom. We also know that the partial pressure of any component is equal to the mole fraction of that component times the total pressure. Using that, we can do this. What we've done here is we've just replaced the partial pressure of, say, gas C with the mole fraction of C times the total pressure. Likewise for D, A, and B. Do that, do a little bit of rearranging, pull everything with total pressure over the standard pressure out. And we get the ratio of the mole fraction of C to the C, mole fraction of D to the D over mole fraction of A to the A, mole fraction of B to the B, times that ratio. Raised the power of this is just C plus D minus A minus B, right? C plus D minus A minus B. We're going to call this delta N. And what it is, it's the difference in the moles of the gaseous products and the gaseous reactants, the products minus reactants. We're going to call that delta N, like I said. So that means we can write Kp as equal to K mole fraction times the total pressure of the standard pressure to the delta N, where K mole fraction is just the mole fraction of C to C, D to D, etc. If we rearrange this just a little bit by dividing both sides through by total pressure over standard pressure to the delta N, we get K mole fraction is equal to Kp total pressure over the standard pressure to the negative delta N. So this is how we convert from one K to the other. And in general, they're different numbers unless delta N is 0. What does that mean? That means we have the same number of gaseous products as we do gaseous reactants. All right, molarity. So we know that molarity is equal to moles over liters. So for a component, one of the components I, it's equal to the moles of that component over the volume. Now remember, we're talking about gases in the same container and ideal gases. We're going to treat them as an ideal gas, ideal gases, which means that because they're in the same container, the volume is the same and the temperature is the same for all of the gases. So using the ideal gas law for component I, Pi V equals Ni RT, rearrange this a little bit. If we divide both sides by V, we get this term right here, which is just the molarity of component I. So we get partial pressure of I is equal to its molarity, RT. We can use that now to write the ratio of the partial pressure of that component to the standard pressure as the molarity of that component, RT, over the standard pressure. And we're going to do one more thing, just to keep everything dimensionless, no units. We're going to introduce the standard molarity, the standard state molarity, M0. And that's just 1 mole per liter. So what we're going to do is we're going to take this expression right here and multiply by M0 over M0. And it's going to look like this. There's our one M0, there's our other M0. We do that. We substitute this expression in here for each of the terms in Kp, partial pressure of C over the standard state, etc., becomes this. What we get is all this stuff right here is, we pull it out. It's common to all these terms. The only thing that's not the same are the molarities. So we get the ratio of the molarities, products over the reactants, each raised to the power of their coefficient, times M0 RT over standard pressure to the delta N once more, C plus D minus A minus B, which means that Kp is equal to Kc times the standard molarity, RT, their standard pressure. Now remember, this is 1 mole per liter, this is 1 bar. They're just there to keep dimensionless, everything dimensionless. So this, in terms of doing the actual calculation, this is just RT to the delta N. If we divide through by this expression in the parentheses here, we get, if we want to calculate Kc from Kp, it's just Kp times this expression to the negative delta N. Once more, if delta N is 0, Kp equals Kc, otherwise they're going to be different numbers. All right, so temperature and pressure dependence of these equilibrium constants. So we know from section 6.9 that d ln Kp dt is less than 0. It's negative for an exothermic reaction. And we know that the equilibrium, the extent of the reactant, shifts towards the left, towards the reactants, as you increase the temperature. Likewise, if the d ln Kp dt is positive for an endothermic reaction, and the equilibrium, the extent of the reaction, shifts towards the right when you increase the temperature. You may remember Le Chatelier's principle. You can think about it in terms of that. For an exothermic reaction, thermal energy would be a product. So what Le Chatelier's principle says is that when you disturb an equilibrium, it adjusts to even things out, basically. So if you put energy in that's on the right-hand side, it's going to shift back to the left for an exothermic reaction. For an endothermic reaction, you can think about the energy as being on the left side, the reactant side, because it has to be put in. So if you add more energy, it's going to shift to the right to come to equilibrium. Pressure dependence. So looking at this relationship between Kc and Kp. Kp, remember, does not depend upon pressure, just temperature. So the pressure dependence of Kc is going to be in this term right here. And so that means that if delta N is greater than 0, it's positive, then when pressure increases, this term right here gets bigger, but we're dividing by it because this is negative. So that means that Kc decreases when pressure increases, and that means that the equilibrium, the extent of the reactant, shifts towards the left because the K is getting smaller. If delta N is negative, that means negative times negative makes this a positive. So when we increase this, Kc is going to increase. So when pressure, and this is going to increase when the pressure increases, right? When the pressure increases, maybe to make sure it's absolutely clear, this is P total that we're talking about. Total pressure increases, Kc increases, and the equilibrium, the extent of the reaction, shifts towards the right. And like always, if delta N is equal to 0, pressure does not affect the equilibrium. Kp is equal to Kc.